Section 8.8 has us working with uniform motion and work applications. This is really just a fancy way of saying we are going to work with story problems that are going to involve equations for motion and equations for work. Now, as we see listed here, at the very top with our bullet points, we have our equations for distance and work. Now, if you're noticing, both of these are very similar to one another. The only difference, I should say, was that one has to do specifically with distance that's been traveled or someone's moving on, and the other has to do with work, which is a much more general setup and idea between these two scenarios. It's also a little bit more vague in how we define what work is, but we'll see some examples, at least an example on how to go through that. Now, it should also be stated, as we're working with these problems in these equations in various problems that we have, we are going to be modifying one or both of these equations quite a bit. We tend to see the work equation modified a lot more than the distance equation, but we are going to be modifying both depending on what we need to do with the overall problem. Now, it should also be stated, as we're going through these things, writing them down, manipulating them, and all of that is absolutely crucial based on the information that we have been given in a problem. It should also be noted that the strategy that we are going to go through in terms of how to set these problems up is not one that you are required to do, but I think is very useful to kind of make sense of what the problem is asking us and organize our thoughts before we jump into actually doing some mathematical equations or anything like that, or actually problem solving anything. So with this in mind, let's go ahead and jump into our scenarios and examples. So let's start with our first example. Number 1 says, Tim rode his bike downhill 32 miles down the river trail from his house to the ocean and then rode uphill to return home. His uphill speed is 8 miles per hour slower than his downhill speed. It took him 2 hours longer to get home than it took him to get to the ocean. Find Tim's downhill speed. Now, my recommendation to you with this story problem, and with any other story problem really, I think it's a great starting place to basically tell the story problem again, summarize it or recap it in your own words with absolutely no specific details or specific numbers or anything like that showing up in there. What this does is it gives us a little bit of a very generalized framework to start with the problem, and then we can start building something and building a route to our answer from there. So for instance, for this problem, a reasonable summary could be Tim rides downhill to the ocean and then he rides back uphill to return home. He has some hill or some speed that he went downhill at, some speed that he went uphill at. We don't know what they are, but they're different. It took him 2 different times, one time traveling downhill and a different time traveling uphill. And ultimately we're trying to find his speed. So that right there is a reasonable starting framework for this problem. Doesn't tell us anything specific, but at least gives us some general scenarios of what's going on and some general starting points. And the big starting point that we're noticing is that there are really 2 scenarios here. There's a scenario where he's going downhill at a speed, and a scenario where he's going uphill at a speed. And we know that that comes into play because we're told something in our next sentence that relates the two. His uphill speed is 8 miles per hour slower than his downhill speed. We also know, based on what's been given to us, it took him 2 hours longer to get home than it took him to get to the ocean. So right there, again, with my 2 scenarios, one going downhill, one going uphill, 2 separate sets of things are happening. Now, I personally don't think it's very easy to keep track of all of that just in our heads, so I would invite you to make a little bit of a table and let's start organizing our work a little bit. So we have 2 scenarios showing up. We have the instance where we're going downhill, and we have the instance where we're going uphill. And now this sounds like a distance, rate, and time problem. There's some amount of distance that's being traveled at some speed or different speeds over some amount of time. So we're going to fill in some parts here. Make this a little bit neater for ourselves. Okay. Now when we're filling in this table, I think it's very good to have, okay, our distance. What's the unit that we're using for distance? In this case, miles. Our time is in hours. And our rate is in miles per hour. I think that's very useful to be on the lookout for. Units attached to numbers. It's very, very handy. So we're going through these things. So now we have our two scenarios. We have downhill, distance, rate, and time, and we have uphill, distance, rate, and time. So all we're going to use is this table to help us organize our work. I'm going to move this over just a little bit. There we go. So as we're told, Tim rode his bike downhill 32 miles down to the river trail. So he went downhill by 32 miles and then rode uphill to return home. So we can make a reasonable assumption that the distance uphill is the same distance as downhill. Nothing tells us that he went on a different route or a different distance or anything like that. So this is a reasonable assumption to make in this problem. Now the second sentence, we're told his uphill speed is 8 miles per hour slower than his downhill speed. So this right here tells me something about the two speeds, but I do not exactly and explicitly know what either one of those are. And that's fine. All this tells us is that when I'm filling in these two squares here, I'm going to have an unknown or a variable somewhere inside of those. So the problem states his uphill speed is 8 miles per hour slower than his downhill speed. So that tells me if I knew his downhill speed, let's just say that that's r, then his uphill speed would be that speed r minus 8, because it's 8 miles per hour slower than his downhill speed. And using a similar amount of logic, we're going to our next sentence, and we're told it takes him 2 hours longer to get home than it took him to get to the ocean. So again, I do not know the exact time it took him to travel downhill or uphill, which means I'm going to have some unknown showing up in both of those. But I do know that it took him 2 hours longer to get home, which we know is the uphill portion, than it took him to get to the ocean. So if I say it took him t hours to get downhill, then the uphill time, or return home time, would be that same time t plus 2 additional hours, because we're told it took 2 hours longer to get home, or to go uphill is another way of thinking on it. Now, the last thing I want to note, and I left this space down here blank for a reason. It's always worth noting and checking for some of these problems, and I recommend putting kind of like a little double line that we have here to fill in and ask ourselves, am I going to have any totals showing up? And by totals, I mean, am I going to be adding miles together to get a total number of miles? Am I going to be adding time together to get a total amount of time that someone was out traveling? Now it looks like in this particular problem we aren't given anything that indicates a total amount of distance traveled or a total amount of time that was given to us, but I do recommend writing this in because that can come in handy as we're going through and solving problems. So that's why I put in this little total question mark. We might use it, we might not. I think it's worth doing at the start of these problems. So now we have a lot of good information here. We have it a bit more organized. We know which numbers and which variables correspond with which parts of the problem. R represents, oops, thing is glitching out here a little bit. We have our downhill speed, we have our uphill speed. Downhill time, uphill time. So now that we have everything in here filled out, we can start making some equations. Remember that our general equation for distance, I'm going to write this at the very top here, that distance equals rate times time, or d equals RT. Now what I can do is I can start making equations out of this thing using this general formula here. So the distance for going downhill is 32 miles equals some rate times some time. For uphill, we know the equation is going to be 32 equals r minus 8, that's the rate going uphill, times the time, t plus 2. And now we have two equations for our two unknowns that we have showing up. Best way we can go about solving this is by using substitution. So we need to find and solve one of these equations for one of the unknowns. We can either solve the first equation for r or t, or we can solve the second equation for r or t. I'm going to solve the first equation because it doesn't look like it has nearly as much complex stuff going on in it. So I'm going to solve this first equation for r. If I'm solving for r, that means I'm going to get r all by itself. I need to divide both sides by t, which is going to give me 32t equals r. And now I can plug this r into my second equation for r here. It should be noted that in this step, if you would like to solve for t instead, that's perfectly fine. All you would do is end up having these two variables reversed from one another. But the rest of the process and what we're going to do next is the exact same. So I'm going to move us down here to have a little bit of space to work through this problem. It'll let me. Okay, there it goes. So my new equation is going to be 32 equals 32 over t minus 8 times t plus 2. And now I'm going to solve this resulting equation using all of my previously learned methods. So I'm going to use the distributive property and do 32 over t times t, and then 32 over 2 times 2. Which is going to give me 32 plus 64t. We're then going to multiply negative 8 through to t and negative 8 through to 2. That's going to give us negative 8t minus 16. I'm going to combine like terms on the right-hand side of this equation. I'm getting 64 over t minus 8t plus 16. I just added 32 and negative 16 together. And now I'm noticing, well, I have an equation showing up, but I've got a denominator here with a variable in it, and I've got fractions. Our trick to eliminate fractions with all equations is to determine the lowest common denominator amongst every single fraction in the problem and multiply both sides, meaning all terms, by that lowest common denominator. So in this case, the lowest common denominator is going to be t, which means every single thing in this equation is going to get multiplied by t as well. Again, the intention behind this and why we're writing it out this way is specifically to eliminate fractions. Again, when you're doing this, I'd recommend actually showing all of the steps. Actually showing that each individual term is being multiplied by t. The main advantage to this is we're going to have the t's cancel here, and everything else is going to multiply out normally. But I think it makes it clear what's canceling out and how every single thing is changing. And now I'm noticing that I have a quadratic equation. I'm going to solve this thing by our method that we learned in 7.6. I'm going to get everything in standard form, meaning I need to subtract 32t from both sides. And I'm getting 0 equals 64 minus 8t squared minus 16t. I'm going to take an extra line just to do a little bit of a rewrite, get this thing more officially into standard form. We have here. And now I'm going to solve this thing using factoring. You can use other methods if you are aware of them, but up till now, if you're following the course as it's been written and as we've gone through this, we're going to use and solve this thing by factoring. So the first thing we do with factoring is we are going to factor out the greatest common factor. I'm going to move us up here to the very top because I'm running out of some space. I'm going to try and keep the work a little bit together. The greatest common factor amongst all those terms is -8. My recommendation to you is, if you're thinking just 8, well, I have this negative sign out front here. I'd recommend factoring out this negative as well if the leading coefficient in front of the squared term is a negative number. It makes the rest of our factoring process a little bit easier. So now I get -8 is equal to t squared plus 2t minus 8. I can factor that further into t plus 4 times t minus 2. And then I'm solving each of these for where I'm going to have potential values of t showing up in this problem. So my two potential t values are going to be -4 and +2. Make that a better -4 here. There we go. Now in the context of this problem, I can only have one time that's being used. And we can't have a negative time showing up in this problem at all because that's just not realistic. So we have to use a time of +2 here. Now we might think of this and come back to our original problem, which is written right above, and say, well, great, I found time, but I'm asked to find his downhill speed. I didn't find that here. Well, while we didn't find that downhill speed, we do have an equation that we modified that helps us find that. You can also use either of your original starting equations to find that remaining time as well. Either option works. So I'm going to use this one here, this 32 over t equals r. So I'm just separating my work out just a little bit here, just to show that I've got a different part. So I'm doing 32 over r is equal to t. I'm plugging in this 2 that I found. Oops. Oh, I reversed them. It should be equals r and divided by t. There we go. Now I got it. So this 2 is going to now go into this, replace this t down here. So I get 32 divided by t equals r. That tells me that the speed, or the rate that was traveling at, is 16. Now I'm double checking for myself. R represents what? R represents the speed or the rate traveling downhill. That's what I'm asked to find. So, excellent. I have my final answer. That's the speed that he was traveling downhill is 16 miles per hour. Zoom us out here so we can get a look at all of the work. But there's our process for setting up and solving example problem number 1. Looking at our second example, we're told Tony Stark in his Iron Man suit can fly 1,210 miles against a 25 mile per hour headwind in the same amount of time he can fly 1,694 miles in a 25 mile per hour tailwind. We're told to find the speed of Tony Stark flying in his Iron Man suit if there was no wind. So a quick point of clarification here with our idea of a headwind and a tailwind. Hopefully a little visual will help out with this. I'm by no means an artist, so use your judgments as you see fit, or be kind with them. So let's say we've got Iron Man here, and he's going to be flying in this direction. A headwind would imply that the wind is coming at him, so we have the breeze coming at him in this regard. So that would imply that the wind is pushing against him and therefore slowing him down. In contrast to that, if he has a tailwind, it's assumed that the wind is, there we go. It's assumed that the wind is at his back and pushing him forward, and therefore it would be increasing his speed that he's traveling. So once again, like we had in our previous scenario, or previous problem, we have an instance where we have tailwind, or a headwind I should say, and we have the instance where we have a tailwind. So two situations showing up here. So like we did previously, I think it's very helpful to set up a table with this, just to organize our work, organize our thoughts a bit. So we have, the first one was listed with the headwind. Okay. And the second one that was listed was the tailwind. Let's make that extra part down here. Maybe I'm going to have totals showing up. Sometimes we will, sometimes we won't. It depends on the problem. Now we'll make our columns for our distance, our rate, and our time right here. So now we can start filling some things in accordingly based on the information that's been given to us. So first and foremost, we've been told, and we want to fill in these main 6 parts of our table here. So what are we working with? We're told he can fly some amount of speed or some amount of distance. Yeah, he can fly 1,210 miles against a 25 mile per hour headwind. Okay. So that tells us some information about the headwind portion of this. So let's fill those in accordingly. So we're told 1,210 miles. I should fill in miles here. Make this a better distance here. We have our speed is miles per hour and time is in hours as well. Okay? So we're told he can fly 1,210 miles in a headwind. The same amount of time he can fly 1,694 miles with a 25 mile per hour tailwind. So again, underlining, filling some things in here accordingly. Another part within this, it's a little bit subtle, but it's a clear thing that's showing up with our time column, is we're told in the same amount of time. So that tells us that the two times that we're going to have here are the exact same. I don't know what that time is, but I can at least fill those in as saying they both have the same unknown time of t with that. Now we need to fill in this middle column here with our rates. The question is asking us to find the speed of Tony Stark flying in his Iron Man suit if there was no wind. So we can think of that as he has some speed r. Now if he has a headwind that's moving against him, so that speed is going to be decreased by 25 miles per hour. If he has a tailwind, then that speed is going to be increased by 25 miles per hour. You can see a similar setup with this where we have something adding to a speed or taking away from the speed in other problems where maybe you have a boat going with a current or against a current, upstream, downstream, things like that. All different ways of saying that we're going to be adding to the rate or subtracting from the rate. We also have nothing in the problem indicating a total amount of mileage is necessary. We have nothing indicating that we're going to have a total time showing up here either. So we don't really need to worry about this part of our table for now. We'd like to start off with it just to have it filled in, but it's not always necessary. And now I can start building some equations out of this thing. Again, I'm remembering back to my regular distance is equal to rate times time equation. So I'm filling things in here and making some equations. I have 1,210. There we go. Times rate times time. And I have 1,694 equals this rate times time. Let's make this a better R here. There we go. And now we could look at this and we say, well, looking at it in these two forms, I don't exactly know how I'm going to solve this thing with the equations I've been given. Just moving this over because I'm running out of a little bit of space here. And written in these two forms as they are right now, yeah, it's not obvious how I'm going to solve for this specific speed or rate that he has. But what I do know is that these two times are equal to one another. So what I can do is I can algebraically manipulate these equations by solving each of them for t, meaning I'm going to get t all by itself. And to do that, I'm going to divide the top equation, both sides, by r minus 25. And for the bottom equation, I'm going to divide both sides by r plus 25. That's going to give me an equation of, I'm just writing this down below here just so I can keep the picture up. My first new equation is going to be 1,210 divided by r minus 25 equals t. And then the other one is going to be 1,694 divided by r plus 25 equals t. I know that these two times are equal to one another, so I can set these two equations equal to one another. And I'm getting 1,210 over r minus 25 equals 1,694 over r plus 25. And from here, I can now solve this thing using any method or algebraic methods or procedures that we've learned in the past. Here I'm seeing I have two fractions multiplying together, I should say a fraction equals a fraction, which means I can do cross multiplication. Again, as a reminder with this, cross multiplication can only be done in the situations where we have a fraction equals a fraction. It's a hyper-specific scenario, but if that does show up, like we have right here, then we're free to use this method and procedure to find our answer. Now I'm just moving us up here because I'm running out of space. I'm going to use the distributive property to multiply this thing through over here. And I'm going to use a calculator off screen to do these number calculations because I don't know what these numbers are off the top of my head. And I'm getting 1,210r. And then 1,210 times 25 is going to give me 30,250. Now the other side, I'm doing something really similar. For r minus, and again multiplying 1,694 times 25. I'm getting 42,350 there. Now again, the numbers might look big and gross and terrible, but we've got a calculator. We can use that as we're going through these problems. So now I'm solving for r. I'm going to subtract the smaller of the two variable terms from both sides. It's going to mean I'm never going to divide by a negative at the very end of this problem, which is rather nice. What does this calculation be? It's 1,694 minus that. That's going to give me 484 r. And then I'm going to be adding this 42,350 to both sides. That equals, we have 484 r on the right side. And let's see what these two things are when they add together. I'm getting 72,600. I'm dividing both sides by 484. And when I do that, I'm getting 150 equals r. And again, r represents our speed that he'd be traveling if there is no wind at all. We can check up at our table and see, does that make sense with what we have written up here? Yes, that does. Does it make sense with the picture that we drew over here? Yes, that does. So, therefore, we have our final answer, and we are good to go. Our third example that we have here is a bit of a different type of question that we had previously. So we're now moving into the realm of working with work problems. Remember, our work equation is very similar to the distance equation, The difference is that we're going to have work is equal to rate times time. Now, what we define as work is a much more abstract and weirder sort of thing we're looking for compared to a distance. A distance is normally how many feet, how many miles, how many centimeters, how many kilometers, something like that. Work doesn't really have a lot of conventional units that are associated with them. As a result of that, we're going to need to dig a little bit deeper into finding what those are and be on the lookout for any buzzwords that tell us what the work is as we go through these problems a bit more. Quick examples of what work could look like could be the number of lawns mowed, the number of houses built, the number of walls painted. We can kind of get an idea of you're doing some sort of work to accomplish something or get something done. So keeping that in mind, looking at our third example, we're told Ron Swanson can clean his cabin in 6 hours. His friend Andy volunteers to help him to avoid doing work at the Parks Department. Working together, they can clean the cabin in 5 hours. How long would it take Andy to clean the cabin by himself? So similar to our distance, rate, time problems, we're noticing that we have, in a very roundabout way, 3 scenarios showing up. We have the instance of Ron Swanson cleaning the cabin. We have the instance of Ron and his friend Andy helping him to clean the cabin. And then we have the instance where we're asked about how long would it take Andy to clean it by himself. So like we did with our previous ones, we're going to go ahead and make a table with this. So the instance of just Ron working through these problems, or working through this, we have Andy working on this, and then we have when they do it together. I've also seen people write in this last one as combined, if they want to call it that, but whichever way works best for you. We have our work, we have our rate, and we have our time. So now let's go through and let's start filling some things in here. What's a little bit more unique with these ones, and as we go through them, again, we want to try and find what are our units that we're working with. Well, our units for time are hours. We're good there. What are our units of work? Well, everything seems to revolve around cleaning the cabin. So a clean cabin here, clean cabin here. So the units of work that we are working with are clean cabins. And then our rate is going to be, I'm going to do this in shorthand, but it's going to be clean cabins. I'm just going to do CC with that, per hour, or hours. And now we can start filling in this table with the information that we know. So we are told Ron Swanson can clean 1 cabin, so he has 1 clean cabin, at a time of 6 hours. We're told working together, they can clean 1 cabin in 5 hours. And now we're being asked how long would it take Andy to clean the cabin by himself. So it would take Andy some amount of time, T, to clean 1 single cabin. We don't know what that time is. That's okay. That's quite literally what we're being asked to solve for, and that makes sense then. So now we need to go through and figure out how we're going to make an equation out of this. So this is where we generally are going to end up having to use this middle column more often than not, our rate column, to end up finding the answer. There's no way we could add work together to say 1 cabin plus 1 cabin is 1 cabin. That just doesn't make sense. And we can't have 6 hours plus T hours is 5 hours. Again, doesn't make sense there. So to solve this thing, we're going to need to make an equation coming from the rates here. So we need to figure out how we're going to find the rates for these guys and what they're working at. So that's going to involve us taking this original equation that we have here at the very top, and we're going to rewrite that into and solve that for our work rate. So that's going to look like the amount of work over time equals work rate. So with that, I'm now going to bring that together, specifically this work divided by time into this column here. So Ron does 1 cabin for every 6 hours. Andy does 1 cabin for every T hours. And together they can do 1 cabin in 5 hours. So we know Ron's individual work rate plus Andy's individual work rate equals their combined or total or together work rate here. So we have 1/6 plus 1 over T equals 1/5. And now that we have our equation, we can go through and solve this thing using all of our previously learned methods. I have fractions showing up, so I want to get rid of those. So I need to find what's the lowest common denominator between everything here. And that's going to be 30t. So now that I have the lowest common denominator, I can multiply every single individual term in this problem by that lowest common denominator, and that's going to result in all of the fractions being eliminated. I should note this process of eliminating fractions like we're doing here can only be done if we are starting with an equation, meaning I have an equal sign showing up in my problem at the very beginning. So now I'm canceling things out. The first one I'm seeing the 6 and the 30, they can cancel. 30 becomes 5, 6 becomes 1. Second part, the two t's cancel, they each become 1, nothing happening there. And then our last one, the 5 cancels to a 1, the 30 cancels to a 6. I'm getting my new equation of 5t plus 30 is equal to 6t. Again, I'm solving for t, so I need to subtract 5t from both sides. I'm getting that 30 is equal to t. Now t represents, making sure we're going back to our table here, t is the amount of time it takes Andy to clean 1 cabin. Is that what I'm asked for? I'm asked how long will it take to clean the cabin by himself. Okay, so 1 single cabin, great. That's all I'm asked to do. This number and the variable all aligns with what I'm asked to do in the end of the problem. And now I have my final answer, 30 hours. So for our number 3 bonus version, I'm going to slightly modify the previous one, so a lot of the setup is going to be very similar. But we're told with this one, we have Ron Swanson can clean his 3 cabins in 6 hours. His friend Andy volunteers to help him to avoid doing other work at the Parks Department. Working together, they can clean the 3 cabins in 5 hours. How long would it take Andy to clean 1 cabin by himself? So again, like we did with our previous problem we had here, we are going to set up a table for ourselves. And we're going to use the same labels that we had showing up there. So we had Ron, we had Andy, and we had them together. And like we did vertically, we're going to have our work, and that was going to be clean cabins. We have our rate. We have our time. Bring these in line here a little bit. There we go. Time is in hours, and the rate is once again going to be clean cabins per hour. So we're going to go through and fill this in the exact same way as we did before, but I just want to highlight that we can have different numbers showing up in here. So for this problem, we know Ron can clean 3 cabins in 6 hours. We know together they can clean 3 cabins in 5 hours. We're being asked, how long would it take Andy to clean 1 cabin by himself? So we have a couple ways we can write this out. We can either write in for the how many clean cabins Andy's working with, we can either write this in as 1 or 3. If we want to stay consistent with what we have elsewhere in the problem here, in the information given to us, we could write in 3. For what the problem is asking us, we're only going to be working with 1. So I'm going to list in he cleans one cabin at a rate of R hours. So now once again, I need to create my equation using the 3 rates here, just like we did with our first number 3 problem. I'm going to write each of these in as fractions. So I have 3 cabins for 6 hours. That's one rate. I have another rate of 1 cabin every R. Actually, we use T. T hours to make that better. And then together they can do 3 cabins in 5 hours. And again, I'm still just going to make the equation of I'm adding these 3 rates together. Even though the numbers are slightly different from one another, that's still fine. Now I have this equation and I go through and do the same thing. I'm going to try and figure out how to get rid of the fractions. So I'm going to multiply everything by that lowest common denominator of 30t. Every single fraction is going to get multiplied by that. Again, I'm doing this to eliminate fractions. And now I'm canceling out denominators where I can. The 6 and the 30 cancel. The t's cancel. And the 5 and the 30 cancel here as well. And what I'm left with is 15t plus 30 equals, I think that's going to be 18t. Yeah, got that there. Now I'm solving for t, so I'm going to subtract 15t from both sides, get rid of the smaller one, prevents division by 0. I'm getting 30 is equal to 3t. I'm dividing both sides by 3. And I'm getting 10 is equal to t. So now I know that it takes Andy a total of 10 hours to go through and clean one single cabin. If we were asked, how long would it take to go through and clean maybe 2 cabins or 5 cabins or something like that, we would simply take this time that we have for one cabin and multiply it by 2 or 4 or 5 or however many we are asked about in the context of the problem. But I just wanted to show this as another example of how we could set this thing up if we had some different numbers written in at the very beginning of the problem. And a large part of it is going to be following the exact same process. So bringing things back together, the last a little bit of the notes that we had with section 8.8. We had our 2 main equations that we are using here. We have our distance equation and our work equation. Both of those being distance equals rate times time and work equaling rate times time as well. Remember that we are going to be rewriting and manipulating these things quite a bit, as we saw with a lot of our examples. But start off with these things, take some time to write things out in a table or some other organized way that makes sense to you, and then figure out how these relate to an equation or other equations that could be brought into the problem. Take it slow, take it steady at the beginning of these things, and then I think you'll be looking pretty good with this material.